You know, we all trust cryptography to be this unbreakable vault for our digital lives. But what if the strongest locks in the world could be picked, not by breaking them, but by just listening to them click? That's the secret backdoor we're going to explore today. These tiny, unintentional flaws that can bring down even the most secure systems.
So I want you to imagine a perfect, uncrackable safe. But what if the sounds of the tumblers falling into place actually gave away the combination? That's exactly the paradox we're diving into. It turns out perfect math isn't nearly enough if the machine doing the math is accidentally broadcasting its secrets to the world.
And that brings us to this whole idea, the side channel attack. See, instead of a loud, brute force assault on the front door, attackers are basically eavesdropping. They're listening to these side channels, these little information leaks to find a quiet way in. They're not breaking the encryption, they're spying on the process itself.
So, what are these leaks really?
Well, they can be almost anything. We're talking about tiny, tiny variations in how long a calculation takes, or subtle fluctuations in how much power a chip is drawing. It could even be the faint radio waves or the high-pitched sounds a computer makes while it's just doing its job. Every single one of these can be a clue for an attacker.
Okay, first up, let's look at some of the methods that honestly sound like they're straight out of a spy movie. Attacks that can snoop on hardware from a distance without ever laying a finger on it.
First, we've got the acoustic attack. This is literally where an attacker uses a super sensitive microphone to listen to the subtle, often high-frequency sounds a device makes while it's working. And yeah, it might sound simple, but the information hidden in those tiny noises, it's kind of astounding.
Get this, researchers have actually shown that it's possible to figure out what someone is typing with scary good accuracy, just from an audio recording of the keyboard clicks. Turns out every key has a slightly different sound profile, and that's all an algorithm needs to piece together your words, or way worse, your passwords.
And then we have electromagnetic attacks. You see, every electronic device you own is basically a tiny, unintentional radio transmitter. These faint radio waves that they give off, they aren't just random noise. They are a direct echo of the electrical signals zipping around inside the chips. If an attacker can capture these emissions, they can essentially create a blueprint of what your device is doing internally.
And this is what makes it so incredibly dangerous. An attacker doesn't even need to be in the same room. With the right antenna, they can literally pull these signals right out of the air from a distance, even through walls. It's a completely invisible, totally stealthy form of digital spying.
Now for a totally different kind of leak, one that's created not by fancy physics, but by a really common, and you'd think innocent, coding shortcut. This one is all about time.
A timing attack is so clever because it exploits the fact that some operations take just a tiny bit longer than others. And when I say tiny, I mean we're talking microseconds. But for a computer, that's an eternity. By precisely measuring how long a server takes to respond, an attacker can slowly, methodically piece together a secret, one character at a time.
Okay, this slide shows the whole problem and the solution perfectly. On the left, you've got the vulnerable code. It's trying to be efficient, right? It checks a password character by character and just stops the second it finds a wrong letter. But that efficiency, that's the leak. An attacker can just time how long it takes to fail, and that tells them how many characters they got right. Now look at the secure code on the right. It's totally different. It's designed to be constant time, meaning it checks every single character no matter what. So it always takes the exact same amount of time to run, giving the attacker absolutely no clues.
So the crucial takeaway here is this. Security, in this case, actually comes from being predictable. By making sure there's no early exit and that the whole operation takes a constant amount of time, we just starve the attacker of the very information they need to succeed. It's a really simple principle, but it has a massive impact on security.
All right, so we've seen the attacks. They're pretty clever. Now, how in the world do we defend against them? This brings us to probably the most important rules for any developer writing code that has to handle secrets.
What's the most important number in all of cryptography? For a developer, you're looking at it 0. That's the number of custom cryptographic algorithms you should ever write yourself. The golden rule is simple. Never roll your own crypto. It is unbelievably difficult to get right and to avoid all of these subtle little side-channel flaws.
So instead, you rely on well-tested, peer-reviewed libraries like these. The experts who build things like OpenSSL and libsodium have already spent years, I mean years, thinking about side-channel attacks. They've already built in defenses like constant time functions. They've done the hard work for you.
Beyond just using the right libraries, there are other defense in-depth strategies. Of course, keeping software updated is absolutely critical. Isolating sensitive systems, either physically in shielded rooms or just logically in separate environments, can make a huge difference. And sometimes you can even fight back by intentionally introducing noise, like random little delays, just to make an attacker's timing measurements completely useless.
So far, we mostly talked about software defenses, but for the absolute highest level of security, the kind of stuff that protects banks and governments, you have to turn to specialized hardware. So let's take a look at the ultimate digital vault. This is a hardware security module, or HSM for short. The best way to think of it is as a dedicated, fortified computer whose only job in the world is to handle cryptographic keys. It's literally like a bank's safe deposit box, but for digital secrets. It's the gold standard for a reason.
Now here's why an HSM is so powerful. As you can see, the key's entire life happens inside this secure little box. It's born there, it lives there, and, this is the most important part, it never ever leaves. When your application needs to use the key, you send the data to the HSM. It does the secret work inside its fortified walls and then sends only the result back out. The key itself is never exposed to the much more vulnerable main computer.
And these devices, they're built like actual fortresses. They have physical tamper resistance. If someone tries to crack one open, it will instantly destroy all the keys inside, a process they call zeroization. They require really strong authentication just to use them, and they're built from the ground up to meet the strictest industry-compliant standards out there.
So, the ultimate takeaway here is this. Real digital security isn't just about strong math and complex algorithms. It's about defending against the invisible whispers and the faint echoes our devices are creating every single second. Which really leaves us with a critical question to think about. Is your security prepared for an attack you can't even see, hear, or touch?